Guess I'm leaving out gravity. That's okay. It's a space robot. So let's follow trajectory. X1 desired, X2 desired, X2 dot desired. So I'm find my error, E1 equals X1 minus X1 desired. And E2 is equal to X2 minus X2 desired. So my sliding mode, I'll define as Z equals lambda E1 plus E2, where lambda is just a positive constant. So you can see right away this control method is a little easier to deal with things. Designing a trajectory planner, trajectory tracking control, whereas that E equals X transpose PX method, I just stuck to a regulation control because things get complicated really fast as soon as you do something different with that. But this one is a lot easier to use. So I'll do V equals 1/2 Z transpose times M times Z. Remember property of inertia matrix? When I did the robot dynamics, is that we have the fact that it's basically bounded above and below. So M min and M max are positive constants. Basically because M has a cos X1 term in there, so X1, it's not like there's X1 squared in there. So basically the effects are bounded. So E is positive definite decrescent. So as soon as I write this part here shows me it's positive definite, and this part here shows me it's decrescent. Right? So you can see right away. So it's kind of a valid Lyapunov candidate, valid control Lyapunov function.
So finding the Lyapunov function is kind of easy, right?
Not a control system. Like a real Lyapunov function is kind of like a guess, yeah. But in control
But
systems,
I mean, for tuning flexible chemistry, you can try to guess the Lyapunov and see if it is.
yeah. Well, like I did that for the pendulum. I put like a, what did I put? I put like a 1 plus cosine in the Lyapunov function for the pendulum, right? To prove that it was stable. So you can do the same thing for a robot. But in control systems, much easier to use a control Lyapunov function. You can just force that to use it out. Mathematicians get into trying to find Lyapunov functions for things. Not engineers too much. Half here, half here. I had it and I scratched it in. I'll rewrite it back in. But M is symmetric. So I can write E dot equals Z transpose M, Z dot plus 1/2 Z transpose M dot Z. So just extending that. This is what I'll get. So it turns out it's not quite the best solution to just cancel out all these terms. So at first glance, you may just think, I'll just make u equal to negative this, positive this, positive this, positive that, negative that, and just cancel out everything and then add in a linear feedback term. But remember, this the idea here is that these Coriolis and centrifugal terms aren't really doing any work to your system. They're forces that you feel if you're riding the robot. If you're going for a ride in the robot, you feel them, but they're not actually doing any work. So, you kind of want to avoid trying to cancel those out because they're not really doing too much. So remember, we can take advantage of this skew symmetric property to avoid canceling out things we don't have to cancel out. In this case, with the trajectory tracking, it doesn't work perfectly, but we get some advantage for it. So if I rewrote this as then this term here and this term here basically cancel it to the skew symmetric property. So it doesn't work quite perfectly for trajectory tracking because you still end up with this term here that you have to cancel out, but it is a bit better to do it this way. So my control, now I can just cancel it on these nonlinear terms.
you say one more time why that term is equal to 0? It's similar.
Here?
Yeah.
Oops, I wrote this wrong. The physical meaning is that these are Coriolis centripetal forces, so they're not actually doing the work in the system. So forces that are doing work are the friction and your control force. They're actually doing work to the system, so they should end up in here. But you should expect to see fictitious forces kind of disappear from our lab analysis. Now, it's absolutely true in regulation, where you just want your robot to stick in one particular spot. But you see, when we're doing trajectory tracking, it's no longer exactly true. You still have to compensate a little bit for these Coriolis centripetal terms now when we're doing trajectory tracking, because they will actually cause a bit of an error. But normally, the Coriolis centripetal forces are doing any real work to your system. So we would expect this to be 0. Yeah, I mean, like this isn't really, this term isn't doing any work, and this term isn't doing any work, right? Now, this term appears like it's doing work. That's mostly because we're traveling along this trajectory. So it's kind of like the trajectory is doing work almost. Okay, so if I do that, if m hat equals m, c hat equals c, d hat equals d, then v dot equals negative z transpose k z is negative definite, and therefore z equals 0. It's uniformly asymptotically stable. And if I go to z equals 0, x1 and x2 also go to 0 because they'll be on the sliding surface. So now let's look at robust control for this. Let's look at the case right here whenever. You gotta yell fast. I'm gonna pick up my brush. So let's look at robust control. So suppose we have estimate of friction d hat of x2 is good. And I know the d max, where we have norm of dx2 minus d hat being less than or equal to d max for all x in d. So I kind of have this friction estimate. So when I say for all x and d, in this case, there's probably some maximum velocity I could reach, well, still be less than d max. But if I went over that velocity, I'd probably be d max. So probably this region is really better. Having a maximum velocity, but this is going to be valid. Okay. So then, I have my v equals z transpose m x1 z. I get v dot equals Z transpose F minus dx2 plus U, where F with all these nonlinear terms I put in here before. So choose control, U equal F hat plus D hat minus KZ minus D max Z over the norm of Z. So this is basically what you use instead of sine Z when you're talking about vectors. But it's the same idea. But I can't say sine Z if Z has like two elements in it, right? But this will have the same effect as sine Z. So if F hat equals F, and I get V dot equals negative Z transpose KZ plus Z transpose D hat minus dx2 minus D max Z transpose Z over the norm of Z. In that case, E dot is not less than or equal to negative Z transpose KZ, and E dot is negative definite in D. So the idea here is that this term is going to be greater than or equal to this term, and this term is always negative. Okay. So remember, I do have a region of attraction now. So D, you're probably talking about a maximum velocity where this is valid. But remember, I would have to actually calculate a region of attraction. So my actual region of attraction would probably be even smaller velocity that I'd be allowed to have to make sure that it's asymptotically stable. If I did get beyond that velocity, then it wouldn't be valid anymore. So it's not like it's valid for any trajectory. I certainly couldn't design a trajectory that would take me out of my region of attraction. It wouldn't be stable anymore. So I definitely have to calculate the region of attraction in this case to make sure my desired velocity stayed within it for everything to be still valid. Make sense?
So how can we calculate D max now?
Calculate D max.
Yeah, the maximum. Or is it can be obtained by the experiment?
Yeah, it's kind of like you have to do an experiment. So you're trying to make an estimate of how much your friction estimate could possibly be off from real friction. So I mean, you have a kind of an idea of what real friction is. So you should have basically an estimate of what's the worst case scenario, how far could you possibly be off in your friction model. That's probably pretty achievable. And then, like I said, this could be like, a chattering control. So it might not be the best. So if you want to smooth that control out, you use U equals F hat plus D hat minus KZ minus D max and Z over the norm of Z plus epsilon, where epsilon is a small positive constant. And one can show Z is uniformly ultimately bounded in that case. So this just smooths out that discontinuous signal, so it's not quite so bad anymore. So in the old case, you had like sine z is like, sine z term is like that, right? It's like discontinuous. If you add in this like plus epsilon in here, basically it gives you a little smoothness to it. So it kind of goes close to that, but not quite. So it's a bit smoother. But you get uniformly ultimately down to signal. So you can't guarantee you get to the sliding surface anymore. So the nice thing about this, it's negative definite, z equals 0 is asymptotic stable. You will get to that sliding surface and all your states will go to 0. But in this case, things just end up being bounded. So you pay a bit of a price for adding that smoothness in here. Like I said, that's what you do if you're worried about chatter, or if you're trying to apply this control where you have like valves as your actuators or something other than electric motors that you didn't want to wreck. But you still want to have like a robust control like this.
So if we change the sign to that function, can we say that we can jump from uniform assembly to the uniform UUB to uniform assembly stable?
Yeah, this one's uniform and asymptotically stable.
Yeah.
But if you apply this one, it will be bounded. Uniformly ultimately bounded.
So I'm saying that if we try to make the discontinuous function to continuous one, can we say that we have uniform assembly stable?
No, as soon as you get away from the discontinuity, you end up with things that are bounded. You basically have to be discontinuous to ensure that you're asymptotically stable. Okay, so let's learn another method now for robust control. That would be nonlinear damping. So this is another method that's continuous. So in this case, dn will be positive constant. So this is my robust control term in this case. And you can see it has a couple of advantages over the previous one. One of them is that it's continuous. It's not sharp near the origin, so you're not going to end up with control signal chatter or anything. Because even that previous one that I put up there with like the plus epsilon, you still get quite a bit of control effort near the origin. So it's not even close to being like an optimal control in any sense of the word. But this one is quite smooth near the origin. It just grows when you get away from the origin. So obviously as the velocity goes up, this term would quite increase. But if you're close to zero error, this term does almost nothing. So it's kind of nice that way. So with the other method, you're kind of applying really large controls when you're close to the origin. So when you're really close to zero, you're applying these really large changes in control. This is kind of the opposite. When you get away from the origin, that's when you would start increasing the control quite a bit to try to get back to the origin. So it's kind of the opposite idea almost of the discontinuous control. And the other nice thing in here is that I could just pick dn to be any constant. Last time I had to put some work into figuring out what Dmax was, maybe running an experiment or something like that. Figure out a good value for Dmax. Here I can just pick any value for dn that'll work. I can just play around. I don't have to have any particular value. So any value will give me stability as well. So then I get, so again, let's just assume f hat equals f. Then dot is equal to negative k z transpose kz plus z transpose d minus d hat, sorry, d hat minus d x2 minus dn norm of x2 times z transpose z. So v dot is less than or equal to negative z k min, minimum eigenvalue of k, or the smallest gain in the diagonal k matrix, times the norm of z times the norm of x2 minus dn times the norm of x2 times the norm of z squared. In this case, I don't actually have to know Dmax. Last time I had to know what Dmax was to design the control. In this case, if I know the value of Dmax, so I can analyze the stability, but I don't need it to actually design the control. Okay. So that's kind of the difference here. So I get v dot is less than or equal to minus norm of z squared k min plus x2 times z minus dmax minus dn times z. Then v dot is less than 0 when minus plus dmax minus dn times the norm of z is less than 0. In other words, when the norm of z is greater than dmax over dn. So, therefore, z is uniformly ultimately bounded. So now I have a region outside of the region I have v dot less than 0. Right? So things are uniformly ultimately bounded. But notice I can make that bound as small as I want just by increasing the value of dn. So I do have power to decrease that bound arbitrarily, which is good. So I can make that bound really as small as I want by increasing dn. So basically, those are your two methods for designing a robust control. So any questions about robust control? Those are the two basic approaches. So the first approach is kind of a discontinuous term, or a near discontinuous term, that basically has large changes near the origin. So when you're close to zero error, that term is like going very large on both sides of the origin. So that might not be great for an optimal control if you're trying to reduce the amount of control effort. It's actually good, but it is good for performance. So the nonlinear damping is more suitable for when you don't want that large discontinuity near the origin. The nonlinear damping is the opposite. As you get away from the origin, then things start to go up rather quickly in terms of control effort. Whereas if you're close to zero error, then you basically don't even notice the nonlinear damping. Makes sense? Yeah.
Robust control, we train the neural networks before start experimenting. For example, you find the desired trajectory, then try to train the neural networks and then start run the simulation. Or can we do it online also for robust?
For the robust neural network control, so yeah, you can do it all online. But if you have that, so Dmax, for example, Dmax might be rather than an uncertainty of friction, like Dmax might be your neural network error. Is that what you're thinking about? So what's your question?
I'm trying to say that we train the neural networks offline or online. for example, we define the desired trajectory, train the neural networks.
Yeah.
And after we have the neural network weights, we start the simulation for the experimental. Or can we do it online? For example, train the neural networks like the system is running.
Yeah, so if you train the neural network offline beforehand, then it's hard because you have to train it on the nonlinearities, which you usually don't know, right? But if you train it online, then you can just train based on the state error. So it's much easier. You don't actually have to know the nonlinear terms anymore. We'll see that in a couple weeks. We'll get to that. Okay, so there's one last thing I wanted to do before I leave you tonight. And it's not exactly robust control, but it's kind of related. But this is more like a really practical thing. So you'll almost never see this in the literature, but it's like really handy to do. So even if you're copying a paper from the literature and trying to implement their methods, you'll find that if you actually implement this method as well, because you can always do this as well, it'll actually be really helpful for you. Like people don't bother to do it because it's just kind of like, of course you can do it in real life, but they're trying to like prove some particular control system in their paper. They're not going to get into all the details of what you actually do in real life. So with robots, the big thing is, if you want to minimize energy usage, one of the big things would be to not cancel out gravity if it's helping you. So if my robot is here, and I want it to be here, and I have a gravity term in the dynamics, why would I cancel out that gravity as I'm going down? It's just like unnecessary control effort. I could just let the gravity pull me down, and basically I can save a lot of energy. So this is just an example. Why cancel gravity when it's helping? It doesn't just have to be gravity. It could be any nonlinear term in any system. So if your nonlinearity is forcing you towards zero error, why cancel it out? So everything I've written here today, I always kind of assume that I'm canceling out the nonlinearity. But that might not be a good idea. So in reality, you probably just cancel out the nonlinearity when you have to. When nonlinearity is helpful, you probably just leave it in there. So let's see an example of the robots. So I'm going to take all my nonlinear terms and just lump them all into this variable h, which I'm not going to worry about. So this time I'm going to add in gravity. So I haven't done that before. So where h contains all nonlinear terms I wrote previously. Okay, so just look back in your notes and figure out what h is. I'm going to write it like this because I don't really want to have a really sharp transition. So I don't literally want my robot to fall out of the air and then instantly apply a control torque as soon as it hits its desired position, because that would just be like a massive control signal. And also across the origin, that would give me a problem because I'd have canceling of gravity on one side and then zero force on the other side, and then I get some kind of chattering control. So I probably want to still apply my desired gravity term, which is a feed-forward term, right? That's what I have in the robot code that I gave you. I gave you a PD control, or just proportional control, with gravity feed-forward. The gravity feed-forward was based on the desired angle, right? So that's called when you have a control term that's based on your desired reference signal, that's called a feed-forward term. Okay? So this will be my feed forward term, so I want to keep it. Because that will be helpful actually, so I don't necessarily want to cancel out my feed forward. So I'll define delta G equal to my desired gravity term minus my actual gravity term. Okay, so my feed forward term I want to keep, so I do want to cancel out my G of theta D. So I'm gonna cancel this out because that's just a feed forward term, so I want to have that in there. But this delta G here, this is something I might or might not want to cancel out. If it's helping me, then I'll just leave it because it's actually bringing me towards my better position without me having to expend any energy to get there. So I'll cancel out H, I'll cancel out my feed forward term. And this will all happen if this term is basically bad. So if this Z transpose times this delta G is greater than 0, that's like, it's not helping me. So I do want to cancel it out in that case. But in the other case, I could just leave it because it's kind of helpful. So I'm trying to leave this term out. I don't actually want it. But if I just have this here, and then I just have a 0 here, unfortunately that gives me a discontinuous term. I don't want to have a discontinuous term, because then when I put it into my Lyapunov function, I'll get a b dot that's discontinuous, and people will complain that I have a discontinuous b dot, because technically you can't apply the Lyapunov theorems if you have a discontinuous b dot. So I'm just going to have this little smoothing function in here. But the idea of this is to make this disappear. Okay, so I'll try to make this disappear as quickly as I can. So when I used to plot things like this, like 1 plus cos x, I just want to take a quick look at it to remind myself. I think I know what 1 plus cos x looks like, so I'll just like quickly plot it. I used to use easy plot in MATLAB, so I'm going to reuse MATLAB easy plot. So it's like a really quick way to look at a graph. Like, oh, what does sine x plus cos x look like? Just type in easy plot, sine x plus cos x in MATLAB. There's no work whatsoever to plot something for you. But what if you don't have MATLAB open? What if you don't have, you're in like a public library or something, you don't have a graphing calculator on you, you really want to know what this 1 plus cos x looks like without having to work at it too much. You know, you just type this into Google now, and it gives you a little graph. Did you know that? I just discovered that yesterday. I was like, this is so cool. You just have like x squared plus 3x minus 1 over x into Google, and it plots it for you now. So I don't know how long that's been there, but years probably. I just noticed it yesterday. I guess it's kind of cool. So, I mean, I usually have MATLAB open, so it's not a big deal, but I guess I can look at graphs on my phone now really easily. Maybe we'll do that. That's awesome.
You guys should all take advantage of that. You should graph interesting things on your phone when you're bored, instead of playing games, messaging.
Alright, so A here is kind of a large positive number. My variable A is a large positive number. Note smoothing function. S is necessary to ensure continuous B dot. But basically picking A kind of as large as possible essentially makes it a discontinuous function, and basically so if H hat equals H and G hat equals G, then B dot is negative semi-definite, or sorry, negative definite, and he's less control effort. Than before. And if you do this, you'll find out that you not only use less control effort, actually your performance will actually improve. So it actually turns out trying to cancel out all the nonlinearities is not actually real good for performance. If you can identify when those nonlinearities are helpful and just let them be, turns out your performance will actually improve. So it's actually improvement both in performance and reducing control effort. So it's one of those win-win control scenarios in control systems, which is good. Because often there's kind of a trade-off between control effort and performance. So this is one of those situations where you get both better performance and less control effort. So it's kind of that's what makes it a really useful technique. So like I said, when you read papers in literature, they probably won't do this, but once you've implemented your control system, doing this as kind of the last step in your controller is really easy to implement. And you'll find that it kind of has a little bit of a dramatic improvement. So it's kind of a neat trick. So next week we'll get into adaptive controls. We'll see how to make controls adapt in large uncertainties. So today's lecture was more for like small uncertainties in your system. You kind of almost know the model, but not quite. So next week we'll do the adaptive approach where you really don't know the model at all. And down to these huge uncertainties. Okay? All right, we'll see you next Monday.